Okay, welcome back to exponential functions. Let's take a look at the graph of y equals 3 to the x minus 2. Now this isn't quite exponential because of this minus 2. Without the minus 2, it fits our definition of an exponential function. The minus 2 makes it not exponential, but it's closely related. Alright, again, we're going to build a table here, plug some numbers in. 3 cubed is 27. 27 minus 2 is 25. 3 squared is 9. 9 minus 2 is 7. 3 to the 1 is 3. 3 minus 2 is 1. 3 to the 0 is 1. 1 minus 2 is negative 1. And then it gets a little ugly, because 3 to the negative 1 is 1/3. And 1/3 minus 2 is how much? How about negative 5/3? Plug in negative 2. 3 to the negative 2, again, remember negative exponents are going to give us fractions. That's going to be 1/9 minus 2. Let's see, that's 18/9, so I think it's negative 17/9. And then finally, 3 to the negative 3, that's 1/27. And then we have the minus 2. That would be 54, so 1 minus 54 would be minus 53/27. Okay, so our graph, start with the nice numbers. 0, negative 1, 1, 1, 2, 7, 3, 25, way up off the grid. And then these ones. Negative 1, negative 5/3. Let's see, that's right about there. Negative 2, negative 17/9. It might be helpful to have negative 17/9 as a decimal. And we see it's negative 1.8888, so it's getting close to negative 2 right there. And then same with negative 53/27. That's even closer to negative 2, but not quite to negative 2. So here's what's happening. Our graph looks like so. Our domain, again, positives, 0, negatives. Our domain is all real numbers. But look at our range this time. What's happening? What's happening is this graph is coming down and getting really, really close to negative 2, and we saw that in these numbers here. So our range is y is greater than negative 2, and then our asymptote we typically draw in as a dotted line like so, is y equals negative 2. Our y values here are getting really, really close to negative 2, but not hitting negative 2. So compare that with what we had with y equals 3 to the x. And what did this minus 2 do? It simply took the graph and pushed everything down exactly 2 units. So this minus 2 out here slid the graph down 2 units. Alright, so conversely, what do you think is going to happen if I do 4 times 1/2 to the x plus 3? Well, a reasonable assumption would be, comparing this graph with that graph, that when I plug a number in, let's just try it, like when I plug in 0, when I plug in 0 I get 1/2 to the 0, that's 1. 1 times 4 is 4. 4 plus 3 is 7. When I plug 0 in here I got 4. When I plug 0 in here I got 7. So what's happening here? This plus 3 is simply going to take the graph and shift everything up 3 units. So that makes it easy to fill in the table. The table is going to be exactly the same, but everything's going to be 3 units bigger. So that's going to be 35. That one's going to be 19. That one's going to be 11. 3 bigger will be 5. 3 bigger will be 4. And 3 bigger will be 3.5. So our graph looks like so. Drawing some points here. 0, 7, negative 111, negative 219, way up off the grid, 1, 5, 2, 4, 3, 3.5. We still have the exact same graph, the same exponential decay, simply shifted up 3 units. Which means our domain is still all real numbers. Our range shifted up 3 units, so y is now bigger than 3, which means our asymptote is y equals 3. Alright, so summary of what we've seen. If you have y equals a times b to the x, your y-intercept will be 0, a. Your range will be all real numbers. Your domain will be all real numbers. Your range will be positive numbers. And your asymptote will be 0. If, on the other hand, you have y equals a times b to the x plus c, and I'm going to just put plus c, recognize that c could be a negative number. So this could be minus 3 like we saw a few minutes ago. Then your y-intercept, when you plug 0 in, b to the 0 is going to give you 1. 1 times a is going to be a, and then you'll have a plus c. So your y-intercept will be a plus c. Your domain will be all real numbers. Your range will be y is greater than c, and your asymptote will be y equals c. Growth and decay. We have growth when b is bigger than 1. Doesn't matter what the other letters are. And we have decay when b is between 0 and 1. And again, it doesn't matter what the other letters are. And then there's something that we talk about called base multiplier property. And we kind of saw this. I just didn't point it out. Let's say I had y equals 3 times 2 to the x. And I were to build a little table, and I'm going to make life easy on myself. I'm just going to use positive numbers here. When I plug 0 in, I get 3. When I plug 1 in, I have 3 times 2, that's 6. Notice I multiplied by 2. When I plug 2 in, 2 squared is 4. 4 times 3 is 12. Notice to go from 6 to 12, you would multiply by 2. Plug 3 in, 2 cubed is 8. 8 times 3 is 24. To go from 12 to 24, you would multiply by 2. So this is the property of exponential functions. The property of exponential functions is if your x's go up by 1, your y's get multiplied by whatever the base is. Now compare that to a linear function. Again, I'll just pick some easy numbers here. If I plug in 0, I get 1. If I plug in 1, 2 plus 1 is 3. If I plug in 2, 4 plus 1 is 5. And if I plug in 3, 6 plus 1 is 7. So notice for a linear function, you're adding a fixed number each time. Where an exponential function, you're multiplying by a fixed number each time. Okay, and that information is going to allow us to answer the last 2 questions here. It says, input-output pairs for 4 exponential functions are listed in the table below. Complete the table and write the equation of each function in the form y equals a times b to the x. Alright, so we notice this is exponential because we started at 3, we multiplied by 2, we multiplied by 2, we multiplied by 2, so the next one we would multiply by 2, that would be 48. And then our function would be f of x equals, remember that a gives you the y-intercept, so a is 3, and then the base is your multiplier. We're multiplying by 2 each time, so our base is 2, so we end up with f of x equals 3 times 2 to the x. All right, this next exponential function, we started at 64. We divided by 2, which is the same as multiplying by a half. We divided by 2 again. So the next one would be divide by 2, and then divide by 2. Our function would be, our a number is 64, because that's our y-intercept, and our base is 1/2, because we were multiplying by 1/2 each time. All right, these last two, it looks like I didn't give you very much information, but you really don't need much information for an exponential function. I've got my intercept, I've got my a number, and then I see I multiplied by 3. So the next one would be multiply by 3 again. 6 times 3 is 18. 18 times 3 turns out to be 54. And then 54 times 3, and yes, I am using my calculator, turns out to be 162. So h of x is 2 times 3 to the x. K of x, without even completing the table, I can write the equation. I see that I started at 100, and then I divided by 10, which is the same as multiplying by 1/10. So without even completing the table, all I really need is the y-intercept and 1 point, and I can find the equation. What we'll fill in the table, let's see, I would divide by 10 again, I would have 1. Divide by 10 would be 1/10. Divide by 10 would be 1/100th. All right, our final question in this section. Input-output pairs for 4 functions are listed in the table below. Determine if each function is linear, exponential, or neither. Okay, so again, the way to tell exponential is you multiply by the same number each time. And the way to tell linear is you add the same number each time. So let's see. To go from 50 to 25, if it's linear, that would mean I subtracted 25. So here I would have to subtract 25 again, I would get 0. So this one's definitely not linear because I didn't subtract 25 each time. For exponential, if I take 50 and divide it by 2, I get 25. If I take 25 and divide it by 2, I do get 12.5. And then you can check 12.5 divided by 2 gives us 6.25. And 6.25 divided by 2 gives 3.125. So that one's exponential. We're dividing or multiplying by a half each time, dividing by 2, or multiplying by 1/2 each time. All right, how about the next one? Is it linear? We subtracted 10, we subtracted 10, but then we only subtracted 5. So it's definitely not linear. We're not subtracting the same thing each time. And I think you can tell right away it's not exponential, because what would I have to divide 50 by to get 40? Well, I'm not sure, but I'm pretty sure if I divide it by the same thing, I won't get 30 next. So this one is a neither. This one, I think you can quickly tell this one's linear. Subtract 10, subtract 10, subtract 10, subtract 10. This one's linear. And finally, K, subtract 10, subtract 10, add 10, add 10. That's not linear. We didn't do the same adding and subtracting each and every time. And it definitely can't be exponential because it starts as decay. It would have to continue as decay. It can't turn around and start growing again. So that one's also a neither. All right, so that ends our introduction to exponential functions. We'll be looking some more at exponential functions over the next couple sections.